All right, so in this section, we're going to look at what's called the cross product. If you remember in our last section, we looked at what was called the dot product of vectors. And so in this section, let's take a look at a new one. Now, before we get started here, we have to have a little bit of background about what are called determinants. This is more of a linear algebra term, but it's something that we're going to have to use to compute the cross product. So I'm just going to kind of show you the basic structure of how to compute these. A determinant, it's a function. It puts in a matrix and it spits out a real number. So I'm going to show you how to do it for a 2x2 and a 3x3 matrix. If you have a 2x2, let's just say the entries are A, B, C, and D. If I want to compute the determinant of that matrix, the vertical bars are usually the notation we use. Sometimes you might see the letters D, E, T instead for determinant. But what I do is I multiply the top left entry by the bottom right entry. So I take that product, I get A times D, and then I subtract the product B times C, which is the product of the two numbers in the bottom left corner and the top right corner. So it's kind of like the difference in the products of the two diagonals. Now, so I guess let's maybe go down here. Let's look at example A real quick. My matrix is 1, 3, -4, 5. I'm finding the determinant of that matrix. So what I'm going to do is I'm going to multiply 5 times 1 along the main diagonal. Make sure I subtract, and then I'm going to subtract the product of the numbers on the other diagonal, -4 times 3. So I end up with 5 minus -12. And so I end up with 17. Now, how do I do this for a 3x3 matrix? Kind of interesting. It actually involves breaking it down into these 2x2 matrices and using the same algorithm we just did here. The way it works is you kind of set or fix a row or column. Most common convention is to use the top row of the matrix. So that's how I'm going to show you how to do it. And what you do is you start by looking at the coefficient that's in the top left corner, which we're calling A. And then you essentially cross off the row and column dealing with that specific entry, and you multiply by the determinant of the 2x2 matrix that's left over. So I would cross off the row that contains A and the column that contains A, and I look at the letters or the entries that are left, and I'm left with the matrix made up of E, F, H, and I. So I would multiply by the little 2x2 determinant of that small submatrix. Then I go to the next entry in the row, top row that I used, which was B. I would cross off the row that contains B and the column that contains B, and you'll notice what's left is D, F, G, and I. So I would multiply by the 2x2 determinant of the matrix made up of D, F, G, I, using the exact same order of those entries. The only thing that changes is when you do that middle term, you make sure that you change the sign and you subtract. Every time we do this, we're going to alternate signs. So the first time it's going to be positive, then it's going to be negative, then it's going to be back to positive. If you were using a different row to do this, it would then go negative, positive, negative, and then it would go back to positive, negative, positive. And you can fix a column instead of a row if you want, but most of the time we're just going to use the top row. Okay, so I switch the sign on the middle one, minus B times that determinant. And then last but not least, I'm going to cross off the row and column that contains entry C. And so I'm left with this little submatrix here, D, E, G, H. So I would take C and multiply it by that 2x2, D, E, G, H. And I'm back to positive. So whatever the sign is on C, I don't have to change it. Computing all this is going to end up giving me the determinant for that 3x3 matrix. So let's try that with example B down here. We have the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. And so I'm going to just use the top row. I'm going to fix that row. First thing I'm going to do is I'm going to take the number 1 and I'm going to multiply it by the determinant of what I get that's left over when I cross off row 1, column 1. So that would leave me with 5, 6, 8, 9. And we'll compute them individually in a minute. Okay, next up, I'm going to cross off. Now remember, minus 2. It goes positive, negative, positive. So now I'm going to switch the sign on 2. matrix that's going to be left over, I'm going to cross off first row, second column, 4, 6, 7, 9. Oops, I wrote them outside the matrix. There we go. 4, 6, 7, 9. And then last but not least, I'm going to cross off first row, third column to get rid of the entry that contains 3. And I'm left with the little submatrix back to positive plus 3 times the determinant of 4, 5, 7, 8. And then I'm just going to compute these individually. So I get 1 times, using our algorithm for the 2 by 2, 45 minus 6 times 8 is 48, minus 2 times 9 times 4, 36, minus 6 times 7, 42. And then back to plus 3 times, let's go to blue, 8 times 4, 32, minus 5 times 7, 35. And so I end up with, let's see, 1 times negative 3 minus 2 times negative 6 plus 3 times negative 3. And if you crank all that out, you get 0. And you'll see take a linear algebra class, matrices that have a determinant of 0 are very interesting and have lots of cool properties, but to be continued. This is your short little movie trailer to get you interested in why. 3 extra points to remember about determinants, and these are going to be helpful when we start talking about the cross product in a little bit. You can only calculate the determinant for a square matrix. All that means is that the number of rows needs to be equal to the number of columns. So it needs to be an n by n matrix, meaning that the number of rows and number of columns have to be equal. If you switch any 2 rows of the matrix, or I'm sorry, let's go number 2 first. If any 2 rows of the matrix are the same, then the value of the determinant will always be 0. And then last but not least, if you switch or interchange 2 rows of a determinant, so if you take the matrix and you say reverse the second row and the third row and flop their spots, that's going to multiply the value of the determinant by -1. So these are just some helpful hints to keep in mind when we start exploring what's called the cross product. Still dealing with vectors here. When we did the dot product, we put 2 vectors in. We took the dot product and we ended up getting a scalar as a result as our output. When we do the cross product, it's actually a way to put in 2 vectors and actually still get a vector coming out of it. So what we have here is, let's just take 2 vectors, call them A1, A2, A3, and B1, B2, B3. The cross product of A and B, which we denote A cross B, notice that these are vectors. So if I was writing this on paper, I would make sure to put my arrows above them. It still results in a 3-component vector as a result. So that's one thing that's different about the cross product, is you put in a vector, you put in 2 vectors actually, and you get out 1 vector. Whereas with the dot product, you actually get out a scalar. And then, how do we figure out what all these entries are? The result, it looks like we have A2 times B3 minus A3 times B2, A3 times B1 minus A1 times B3. It just looks like a lot of jumble. The actual easiest way to remember this is it's really easiest when expressed as a determinant. So what I do, and you'll see where we get this exact formula, what I do is I put my standard basis vectors in the top row, I, j, and k, 1, 0, 0, 0, 1, 0, 0, 0, 1. And then I'm going to put the rows of the matrix, or the determinant, are going to be the vectors. So I'm going to put them in order of how they were listed. A was listed first, so I'm going to put A1, A2, A3. And B was listed second, so I'm going to put the entries of B, B1, B2, B3. And I'm going to use our formula to compute the determinant, and you'll see what we get. So if I use the first entry, I have I times, crossing off first row, first column, I would be left with the determinant of this little 2 by 2, A2, A3, B2, B3. Now I switch, minus J times, cross off first row, second column, I'm left with the determinant of A1, A3, B1, B3. And then last but not least, plus K times determinant of A1, A2, B1, B2. So I crossed off first row, third column. And so what we get is we get I times A2B3 minus A3B2 minus J times A1B3 minus A3B1 plus K times A1B2 minus A2B1, just using our formulas from up top for the determinants. And you'll notice if we write this in component form, first one we get is A2B3 minus A3B2. Well, that's an exact match for what we have up here. The second one, now notice we have A1B3 minus A3B1, which is completely reversed from what we have up here. But notice, what do we have in front? We have a minus sign in front of the J. So once we distribute, we're actually going to end up getting A3B1 minus A1B3. Last one. Let's see where we at. A1B2 minus A2B1. That's exactly what we have here. So that is the cross product. Geometrically, let's hold off for a little bit. I'll explain what it means geometrically in a little bit. But you can see it's a lot easier to express it as a determinant. Again, I'll say it again. The cross product of two vectors is a vector, whereas the dot product of two vectors is a scalar. So let's compute one. If u is 1, 2, negative 2, and v is 3, 0, 1, let's find u cross v, and let's find v cross u. That's how we read it. So I'm going to set this up, ijk. I'm going to put u in the second row because that was listed first, and I'm going to put v in the third row because that was listed second. And so I end up with I times, crossing off first row, first column, we're left with the determinant of 2, negative 2, 0, 1. So I end up with 2 times 1, which is 2, minus 0 times negative 2, which is 0, minus j, flip the sign. If it helps you, put the little rule positive, negative, positive up here. Times, okay, crossing off first row, second column, we would be left with, maybe I'll actually do that so we can see it for this one. If I cross off first row, second column, I'm left with 1, negative 2, 3, 1. So we're going to have 1 times 1, which is 1, minus 3 times negative 2, which would be negative 6. Get rid of this. And now we're going to cross off first row, third column. And so we're left with plus k times, we're left with this little submatrix right here. So we're going to have 0 times 1 is 0, minus 3 times 2 is 6. And so we end up with 2i minus 1 minus negative 6 would be 7. And because we have a minus in front, we get minus 7j. And then we get 0 minus 6 would be minus 6k. You can leave it in terms of the standard basis vectors, or you can write it in component form, 2, negative 7, negative 6. Okay. So either of those would be acceptable. V cross u. So think for a minute, do you think it'll be the same result? If we switch the order of the two vectors, should we get the same answer? Well, let's set it up and see. I, j, k. Now I'm going to put 3, 0, 1 in the middle row, and I'm going to put 1, 2, negative 2 along the bottom row. Now, we could compute this if we wanted to do it by hand all over again, but I'm going to direct us back to a little piece of advice from the first page here. Take a look at number 2. I'm sorry, take a look at number 3. If you interchange two rows of a determinant, so if I switch two rows, it's going to multiply the value of the determinant by negative 1. Well, what we did is we switched two rows. We took row 2 and row 3 and we reversed them. So all we're going to do is we're going to multiply this entire vector by negative 1. So this is just going to be the negative of 2, negative 7, negative 6. And reason for that is because we switched row 2 and row 3. So I end up with negative 2, positive 7, positive 6. And if you want to confirm that, go through the calculation like we did in part A, and you'll see that we get the same, or we get that result. How could you check to verify if this is correct? There's a fact I'm going to share with you on the next page, but I'll give you a small preview of it now. The way you can check is by understanding that this cross product, u cross v or v cross u, is orthogonal. If you remember from the last section, that means perpendicular. It's orthogonal to both of the original vectors. So it's orthogonal to both u and v. Okay, so using that fact, how can we actually check to see if we did it correctly? You would check if it's orthogonal, that means that the dot product of your two vectors has to be 0. Well, one of our vectors is u cross v, and it's orthogonal to u. So that means if I take the cross product of u cross v, and I take the dot product of that vector, remember this is a vector, with u, I should get the scalar 0, because now I'm taking a dot product. But it's also, this cross product is also orthogonal to v. So if I take the cross product or the dot product of u cross v with v, because those two vectors are orthogonal, I should also get 0. So it's a good way to confirm if you did your work correctly. And same idea for part B, but instead of using u cross v, you would use v cross u. So we can see from this example, is the cross product commutative? The dot product was commutative. If I switched the order, I got the same answer. Clearly, for the cross product, these are not the same vector, so no. U cross v, it's not equal to v cross u, it's equal to negative v cross u. Okay. They're related, but you just got to remember that negative sign in front. Okay. So what's the significance? Why do we have this strange vector? Well, the significance of the cross product, if you remember, the significance of the dot product was it was a way to almost measure how much two vectors point in the same direction. It gave us a way to calculate the angle between the two vectors. The significance of the cross product is, and we just gave a preview of this on the last page, it's a vector that produces a vector that is orthogonal, in other words, perpendicular, to both A and B. Okay, so this vector is perpendicular or orthogonal to both of the original vectors. Okay, here's a nice little sketch of that. If here's your two vectors A and B, kind of sitting on the ground, then the pink vector pointing up in the air, you'll notice the right angle. It forms a right angle with the first vector, and it forms a right angle with the second vector. That's your cross product, A cross B. And there's your angle between the two vectors. So we'll see in a little bit, there is a formula that relates the cross product back to that angle, just like we had for the dot product. Just another visual over here on the right-hand side. Okay. How do you figure out the direction of the cross product? Those of you who have taken physics, you've probably heard of this thing called the right-hand rule. We have something similar here in calc. The direction of the cross product is given by the right-hand rule. So what you do is if you take the fingers of your right hand, it has to be your right hand, otherwise everything's going to be backwards. So take the fingers of your right hand, kind of put them in the direction of the first vector. So if we're doing A cross B, put your pointer finger, your ring finger, your middle finger, and your pinky in the direction of vector A, and then curl them in the direction of B. So try this with the one on your paper. If you take your 4 fingers, not your thumb, point them in the direction of A, so kind of going in like a southwest direction, curl them in the direction of B, your thumb should be pointing straight up in the air. Should. This takes a little practice, so take a minute and try this. As long as you've got your pointer fingers pointed generally along the same direction as A, if you curl them and stop at B, your thumb should be pointing straight up, and that gives you the direction of the cross product. Try it for the one in the right picture. You're going to have to kind of tilt your wrist backwards a little bit. Don't hurt yourself. There's A, curl your fingers in the direction of B, and your thumb should be pointing in a northwest direction, at least mine is. Okay. So again, this takes a little bit of practice. It'll give your wrist a good workout. Okay. A cross B is going to be in a northwest direction for that one. And I like the joke here. If you're a dog, you have paws. How do you do it if you're a dog? Okay, partner practice. If you're watching this at home, it's going to be solo practice. Take a pause. Use the right-hand rule. Get some practice doing what I showed you with your wrist and your pointer fingers and your thumb. Use the right-hand rule to fill in the following about the standard basis vectors. So there's some very, very nice relationships if you take the cross products of the different standard basis vectors I, j, and k. So pause me for a minute and then we'll check these. Okay, so hopefully you had a chance to try these out. If I do I cross j, well, think about your three-dimensional axes here. The x-axis points in the direction of I, the y-axis points in the direction of positive j, and the z-axis points in the direction of positive k. So I'm going to put my pointer finger, my middle finger, my ring finger, and my pinky in the direction of I. I'm going to curl until my fingers are almost pointing directly to the right, and your thumb should be pointing directly up. So I cross j would be k. J cross k, have your fingers point directly off to the right, curl them until they're pointing almost directly upwards, and your thumb should be pointing out at you, which is the direction of positive I. K cross I, this one's probably the one that hurts the most. Have your fingers point directly up in the air towards K, curl them until they're almost pointing directly out at you, and your thumb should be pointing directly off to the right. So K cross I should be J. If you flip the order, you could curl your fingers all over again and do this, but you could also just use our property from the first page. This would switch 2 rows of the determinant. So this would just change the sign from the one directly above it. This would be negative k, this would be negative I, and this would be negative j. Again, what does this confirm? The cross product is not commutative. If I switch the order of my two vectors, I get an opposite result. How about associativity? Let's think, is A cross B crossed with C the same as A crossed with B cross C? We can pick an example and see if it works. If it doesn't work, then we've already answered the question. So that's kind of what I'm doing here. If I take I and I cross it with I cross J, where the parentheses are around the second cross product, remember I cross J was K. So this would be I cross K. We look up at our chart, I cross K is negative J. Well, what if I put the parentheses around the I's instead of the I and the J? I cross I, fun fact, and you can use one of the rules on the first page to confirm this. If I take any vector and I cross it with itself, when I set up the determinant, I'm going to have 2 identical rows in that matrix. Well, look back. I think it was piece of advice number 2 from the first page. If you have 2 rows that are the same, the determinant will always be 0. Notice this is the 0 vector. Okay? So the 0 vector, because we're going to be doing this for 3 entries. So this would be 0, 0, 0. So in our case, this is the 0 vector. If you take the 0 vector and cross it with any vector, you're always going to get 0. Clearly, negative j, which is 0, negative 1, 0, is not equal to 0, 0, 0. So this confirms that the cross product is not associative. So maybe at this point you're thinking, wow, it's not a lot of things. It's not commutative. It's not associative. What good is this? Well, there is good news. I promise. And this would be a good exercise for later for you to finish and try out just to do some of the algebra. So I'll leave this as an exercise. There are some laws of algebra that do hold, and you can kind of maybe pause me and read through these 6 on your own for a minute. They shouldn't be too shocking. So take a pause, look at these 6 for a minute, just so you get a little bit of information about the cross product. Okay. All right, so the first 4 I would say are, I guess, probably what you would expect. It's distributive. Scalars can be moved wherever you want. This one we actually already explored on the first couple slides. The 2 that I think you're probably going to have to study the most are 5 and 6. Number 5, we're actually going to see at the end, is very much related to some geometry with these vectors. This is what's called the scalar triple product. And there's a nice, easy way I'll show you to remember how to compute this one later. It goes back to determinants. They're very useful. The last one I would say is just one you kind of got to memorize. If you take the cross product of A and B cross C, it is equal to the dot product of A and C times vector B minus the dot product of A and B times vector C. So this one I would just, maybe make some flashcards. All right, let's get into some geometry here. I mentioned that the cross product is related to the angle between the vectors. I'm going to draw a picture. Here's A, here's B. Here's the angle between them, theta. If you remember from last section, we had a formula that said the dot product, A dot B, is equal to magnitude A times magnitude B times the cosine of the angle between those vectors. Well, for the cross product, you'll notice we can't ignore these magnitude bars in front, because if I didn't have those, you have to keep in mind this right-hand side here is a scalar, similar to what I see here. This right-hand side would be a scalar. But the left-hand side, if I don't put the bars, would be a vector, and that's a problem. A vector can't equal a scalar. So it's not that the cross product of the vectors is equal to magnitude A times magnitude B times sine theta, but the magnitude of the cross product, so the norm of the cross product, pen is lagging, there we go. The magnitude of the cross product is equal to the magnitude of A times the magnitude of B, and now we're multiplying by the sine of theta, not the cosine of theta. Another fact about the cross product, if you want to check if two vectors are parallel, any two non-zero vectors, A and B, will be parallel if and only if, very powerful statement, biconditional, if and only if their cross product is equal to 0. Okay. And remember, we also could check if they're parallel by seeing if one of them is a scalar multiple of the other. If that's hard to do, take their cross product. You should always get the 0 vector as a result. I'm going to keep reiterating it's the 0 vector because the cross product has to spit out a vector. It can't spit out a scalar. Okay, so geometrically, what does it represent? The length of the cross product, so in other words, the magnitude of the cross product, A cross B, it is equal to the area of the parallelogram spanned or determined by A and B. So the parallelogram would be created if you put maybe put a little dot where each arrow ends and extend. The area of this parallelogram formed right here is equal to the magnitude of the cross product of A and B. How do we get that? Well, use a little bit of geometry. Here's my base. What is area of a parallelogram? Area of a parallelogram, throw back to maybe your freshman year, is base times height. Well, what's the base of this parallelogram? The base is the length of the vector A. Well, that's the magnitude of A. What's the height? I have to drop the height. That's this little vertical altitude that I'm dropping. Well, using a little bit of SOHCAHTOA, sine of theta, I'm going to call this x right here, would be opposite over hypotenuse. There's my angle theta between the vectors. Opposite x over hypotenuse would be the length of B, magnitude B. And then I'm going to multiply magnitude B over to both sides. So magnitude B times the sine of theta. Well, there's my height. So I'm just going to outline this for you here. This is base. This is height. There's your area of the parallelogram right up here. Kind of sketched out so you can see it with the cross product actually drawn in. What we're saying is that the area of this little parallelogram down here, kind of projected onto the almost XY plane, the area of the parallelogram determined by those two vectors is equal to the length of this blue vector, which is the cross product. So if you were to measure the length of that blue vector, it would be the same as the area of this parallelogram down here on the ground. Okay, so let's do an example. Find a vector perpendicular to the plane that passes through the points P, Q, and R. Well, anytime they're asking me for a vector that is perpendicular, I kind of get an idea that I'm probably going to be interested in a cross product. But I need some vectors in order to do that. If I have 3 points, I'm not going to necessarily put them on the coordinate plane right now. I'm just going to put them over here. I have 3 random points. If I want to create some vectors, I'm going to have to make one vector. I'm going to choose to go from P to Q and from P to R. You really can start at whatever point you want, as long as for both vectors you start at the same point. So I'm just going to choose for convention to start with the first point they give me. Vector PQ, remember how I'm going to find that is I'm going to subtract the difference of coordinates. So I'm going to do all the entries for Q, and I'm going to subtract the entries for P. So I'm going to get -2 minus 1, 5 minus 4, and -1 minus 6. So I end up with -3, 1, -7. And then I'm also going to need PR. Got to start at the same point I did for the first one. Going to the other point, PR, I'm going to subtract the coordinates for R minus the coordinates for P. 1 minus 1, -1 minus 4, and 1 minus 6. So I end up with 0, -5, -5. And I want a vector perpendicular to the plane passing through those points. So if this is my plane, I want a vector that's going to be orthogonal. See if I can draw this in a way where it makes it look orthogonal. Yeah, so I'm going to want a vector that forms a right angle with this one and forms a right angle with this one. Well, what's that going to be? That's going to be the cross product. So I'm going to want either PQ cross PR or PR cross PQ. One of them will point in one direction, one of them will point in the opposite direction. Either one will give you a vector perpendicular. So I'm going to just choose to compute PQ cross PR. So we're going to take the cross product. I'm going to set up my determinant, ijk. I'm going to put PQ in the middle row, since that was listed first. And I'm going to put PR in the third row, since that was listed second. And then I'm going to run through our determinant algorithm to figure this out. So we're going to end up with I times crossing off first row, first column. I'm going to end up with 1, -7, -5, -5 as my leftover matrix. So we're going to get 1 times -5 would be -5, minus -5 times -7 would be 35. Make sure you flip the sign, minus J. Cross off first row, second column, I'm left with -3, -7, 0, -5. So I'm going to get -3 times -5 would be 15, minus 0 times -7 would be 0, plus K. Cross off first row, third column, and I'm left with this little submatrix, -3, 1, 0, -5. And so I'm left with -3 times -5 would be 15, minus 0 times 1 would be 0. So we end up with -40. 15 times -1 would be -15, and 15. Perfectly acceptable answer. This vector would be perpendicular to that plane. What's nice about this is you're not really interested in the magnitude, right? If I was to scale this vector up or down in size, if I doubled its length, it would still be perpendicular to both of those blue vectors. If I cut its length in half, it would still be perpendicular to both of those blue vectors because it points in the same direction. I could even switch the direction. I could have taken the opposite cross product and gone this way instead. Okay. So I could scale this by whatever I want. So I could even, let's say I wanted to divide each of those entries by 5. If I divide by 5, then I get -8, -3, 3. Still going to be perpendicular to both of those original vectors. Still going to be perpendicular to that plane. So that's just 2 examples. Make a note here. Any non-zero scalar multiple of this vector is also orthogonal or also perpendicular to the plane. Because you're not using the magnitude anywhere in the problem. If you're using the magnitude, we'll see like in example 4, it's going to matter. Okay? But if I'm just trying to find a vector that's perpendicular, I can scale it up or down as much as I want, as long as it points in the same direction. Okay. Example 4, find the area of the triangle. Wait a second. We said parallelogram was what we were doing. Well, we'll see. Find the area of the triangle with these 3 vertices. Okay. Use a little bit of geometry here. Let's come up with a plan first. Let's say I have 2 vectors I'm going to create. One of them, I'm going to do what I did in the last one. I'm going to make one of my vectors PQ. Let's do that. PQ. And the other one's going to be PR. I need vectors to do this. So we'll compute those in a minute. But let's say here's PQ, maybe not necessarily drawn with the correct direction, but we'll see how this works. Here's PR. We saw how to make the parallelogram on the last page. If I make the parallelogram, that would be this. That's the parallelogram spanned or determined by those two vectors. And we said to do that, we would need to do area of the p-gram would be magnitude of PQ times magnitude of PR times sine theta. Well, if I just want the triangle determined by these three vertices, P, Q, and R, I'm going to draw a little diagonal here. That splits the parallelogram exactly into two equal parts. Region 1 here and region 2 have the exact same amount of area. So if I want the area of the triangle, all I need to do is take 1/2 the area of that parallelogram. So I'm going to compute the area of the parallelogram, and then I'm just going to remember to divide by 2 or multiply my answer by 1/2. So I'm just going to put stars here. This is going to be our strategy for how we're going to compute this. Okay, let's get some vectors. PQ, -1 minus 2 would be -3, 0 minus 2, -2, 2 minus 0, 2. PR, 0 minus 2, -2, 4 minus 2, 2, 3 minus 0, 3. If you want to pause me and try this yourself, go for it. I'm just going to keep running through it, but feel free to try it on your own to do a quick little check-in for yourself. Okay, so step 1, before I get the magnitude, I need the actual cross product. So I'm going to set up my determinant, ijk, -3, -2, 2, -2, 2, 3. And so let's see what we get here. I'm just going to skip the ijk stuff and just go straight to component form. We're going to end up with cross off first row, first column. We get -6 minus 4 minus, switch the sign, cross off first row, second column. We get -9 minus -4, so -9 plus 4. Cross off first row, third column. We get -6 minus 4. So I end up with -10, -5, so +5, and -10. Okay. You don't want to scale this vector down in size like we did in the last one, because the answer to our problem is not just asking what vector is perpendicular to the plane with these points. It's actually asking, it's incorporating the size of the vector. If we downsize this vector, we're making the magnitude smaller. We don't want to do that. This truly is the vector we want to find the magnitude of. Otherwise, we're going to be finding a smaller parallelogram, which means we're going to be making the triangle smaller. We don't want to do that. We want the actual size of the picture. So don't downsize like we did in the last one. I'm going to even put a comment here. Don't divide by a scalar. Here. Okay, reason, because we actually need to find the magnitude. So magnitude of PQ cross PR, square root of the sums of the squares of the components. So -10 squared will be 100. 5 squared will be 25, and -10 squared will also be 100. Square root of 225 would be 15. Third step, let's get the area of, you could get the parallelogram first and then divide by 2, or you can do it all in one step. I'm going to do the parallelogram first. Magnitude of cross product is 15. We just did that. Last step, I need area of the triangle, which is going to be half of that. So it's going to be 15 over 2. Okay. And I realized up here, this was our strategy, but we never actually found the angle between the two vectors. So the other way of really what we did is we remember the area of the parallelogram is just the magnitude of the cross product, PQ cross PR. So we're just doing half the magnitude of that cross product. We don't have access to that angle. We could use the law of cosines if we wanted to find it. But this is probably, in this problem, oops, we don't have access to the angle, so this is a better strategy to go for. Depends on the problem. Sometimes you might have the angle, you might go for this approach here in green. Sometimes you might not have access to the angle, then go for this with too many colors. Go for this strategy that I'm boxing in maroon. So 15 halves. Okay, almost done here. The last part, we have what's called triple products. I mentioned this a couple slides ago. Property 5, back from, where was it? Property 5, right here. A dotted with B cross C. That's called the scalar triple product. And there's a nice way to remember how to compute it. A dotted with B cross C is actually the determinant of the matrix where you put all of the entries of A along the top row, all of the entries of B along the middle row, and all of the entries of C along the bottom row. So easiest way of remembering this scalar triple product is it's a determinant of the 3 vectors components that make it up. Okay. So this here is a determinant. Geometrically, why do we care about this? The geometric significance of the scalar triple product, it actually gives you the volume of the parallelepiped, the sign volume. I'll show you how you can make sure to make it positive in a minute. It gives you the sign volume of the parallelepiped determined by the vectors A, B, and C. So if I have 3 vectors here, all starting from this point in the bottom left corner, okay, A, B, C, you'll see that this makes up a little 3-dimensional prism where all of the faces are parallelograms. That is what we call a parallelepiped. So this is a 3D prism made up of 6 parallelogram faces. Geometrically, that's what it is. And by finding this scalar triple product, we almost have a way of getting the volume. If it's negative, we just have to remember to take the absolute value. Okay? And that'll give us the volume of this 3-dimensional parallelepiped. So the volume of the piped, parallelepiped, determined by A, B, and C, is given by the absolute value of that scalar triple product, A dotted with B cross C. So find the determinant and then make sure to make your answer positive. Now, what if you get 0? There's no volume. What does that mean? If we find that the volume of that parallelepiped is 0, so if this scalar triple product ends up being 0, what that tells us is that those vectors must lie in the same plane. They must be coplanar. Well, that means there is no 3D figure that's created, right? If they're all on the same plane, for example, if they all look like this, well, there's nothing 3-dimensional about that, right? They're all in the exact same plane. There's no 3D figure. If there's no 3D figure, there's no volume. Okay? So that just means that they're coplanar. So now we have a way of checking if 3 vectors are coplanar. Let's use the scalar triple product to show that these 3 vectors, A, B, and C, given, are coplanar. Plan. How are we going to show that? We don't want to have to sketch them. We're going to show that A dotted with B cross C. I don't really need the absolute value here because if I take the absolute value of 0, I'm still going to get 0. If I can show that this is equal to 0, then I've done my job. Because this is going to tell me that the volume of the parallelepiped is 0. And that's going to tell me that A, B, and C are coplanar. So I always like to go into these problems with a plan instead of just starting my computations. Okay, well, we need to compute A dotted with B cross C. I should put my parentheses there. There we go. Okay, so the way I'm going to do that, I'm going to put my entries of A along the top row, 1, 4, -7. I'm going to put my entries of B in the middle row, 2, -1, 4. And I'm going to put my entries of C in the bottom row. Don't scale these vectors down in size, same as last time. Okay, you're not being asked for a vector. You're trying to get a scalar. You're talking about size here. So you don't want to scale these vectors down in size or you're going to get a different result. Okay. In the case of 0, you actually might not, but don't. It's a bad habit to get into scaling these vectors down in problems, okay? Unless you're asked for a vector that's perpendicular. So let's compute this. We're going to end up with cross off first row, first column. We're going to get -18 minus -9 times 4 would be -36, so plus 36. Oh, not a vector, though. Sorry. This is going to give us a scalar. So maybe let me do this a little bit more systematically. Positive, negative, positive, just to remember our rules here. We're going to end up with 1 times the determinant of -1, 4, -9, 18, minus 4. Cross off first row, second column. We're left with 2, 4, 0, 18. Minus 7, back to... Now, notice I say back to positive. That doesn't mean you make the digit positive. It just means you keep the sign of whatever entry that coefficient has. So it's still a negative coefficient because the original entry was negative. I don't have to flip the sign. Cross off first row, third column, 2, negative 1, 0, negative 9. Come over here. So we get 1 times negative 18 minus 36, minus 4 times 36 minus 0, minus 7 times negative 18 minus 0. Okay. So we end up with I think I have a slight mistake here. Let's see. Negative 18 minus negative 36. I'm sorry, this should be positive 36. Make sure you fix that. So we end up with 1 times 18 minus 4 times 36 minus 7 times negative 18. And so we end up with 18 minus 144 plus 126, which gives me negative 126 plus 126. That is, in fact, 0. So therefore, I'm going to put my 3 dots. You maybe used this in AP last year. The volume of the parallelepiped is 0. Therefore, we answered the question. A, B, and C, we were asked to show their coplanar. Now we know, in fact, that they are coplanar. And that ends my argument. And I think that wraps up this section. So now you have some time to get started on your homework. Happy times with the cross product. See you next time.